Hello everybody, and welcome back to another Big Ideas Algebra 2 lesson. Today we are going to be talking about how to solve these rational equations. We've gotten so familiar with them at this point that it's only natural that we can now solve some of these beyond just simplifying them. So, there are two options we're going to be learning today: cross multiplication and using the least common denominator. But there is something both of these methods have in common, both of which involve removing the denominators from your fractions. Our goal is to not even deal with these funky denominators. If we can just get rid of them, the problem would be so much easier. So we're going to start off by talking about cross multiplication, something that we should be relatively familiar with from middle school. In middle school, we learned the following. We learned that any time you have two fractions equal to each other, you're allowed to cross multiply. Cross multiplying means we multiply the numerator of the first with the denominator of the second, and the denominator of the first with the numerator of the second. And what this will end up giving us is it'll end up giving us two sides of an equal sign, two sides of an equation. X times 3 is just 3x, and 6 times 4 is 24. And we know that if 3x equals 24, we can divide both sides by 3 to get what x is. X should be 8. The principle is the same, even with more complicated rational equations. In the example I provided here, we see that we are multiplying across the equal sign. X plus 1 is being multiplied by 8. That's how you get this 8 times x plus 1 right here. We see that 2 is being multiplied with 3x plus 2. That's how you get this term. And what we're doing is, after cross multiplication, we then just want to simplify and solve like we did in Algebra 1. Getting rid of all the parentheses, getting all of your x's on the same side, isolating the variable, using reverse PEMDAS. So let's see this in action. Let's take a look at problem A. Problem A says 7 over x minus 2 equals 11 over 2x plus 10. Since these are both just one rational expression and another rational expression, we're allowed to cross multiply. So I'm going to multiply x minus 2 times 11 and 7 times 2x plus 10. I'm going to write out the in-between step just so we can see this with parentheses. But when you're doing this in your own head, you're allowed to just multiply these out in your head as well, just writing down what they result in. So this is what we have. 11 times x minus 2 equals 7 times 2x plus 10. We can then distribute into the parentheses and solve. So when we distribute this, we get 11x minus 22 equals, when we distribute this, we get 14x plus 70. To solve then, we just need to get our variables on the same side, then solve. So I'm going to choose to subtract 11x from both sides, resulting in negative 22, because these cancel out, equals 3x plus 70. I'm then going to subtract 70 from both sides. And fair warning, this problem does not end up with nice numbers. Doesn't mean we did it wrong, though. Negative 22 minus 70 is negative 92. And that's going to equal our 3x. And now to finish off the problem, we can just divide both sides by 3. Negative 92 over 3 actually doesn't simplify very nicely. You could write it as negative 30 and 2/3, but I'm just going to choose to write it as negative 92 over 3. That's what x is. We've solved the problem for x. Now, when cross-multiplying, there are a couple of methods we can use to solve this. Let's take a look at problem B, for instance. So, as we go through and take a look at problem B, we see that we have a little bit more of a complicated denominator. So, what we could do is, if you wanted to, you would be allowed to factor these problems out, then cross multiply, and then cancel whatever's the same on both sides of the equal sign. But I want to show you what happens if we just do cross multiplication the regular way. It's not that much longer to do it this way, and it helps us see something that we might not have seen otherwise. So here, we cross multiply. We get the following. We get that x squared plus 4x equals 3x plus 12. I hope you'll forgive me. I just multiplied 3 times x plus 4. I didn't want to write it out with parentheses because that's just an extra step that we don't need. From here, we recognize that we cannot actually get x all by itself. The reason being, we have an x squared. But we learned all the way back in units 2 and 3 how to deal with this. We learned that if we get everything on the same side, making one side equal to 0, we might be able to factor this or solve it using quadratic formula, completing the square, graphing, so and so on. What we get is x squared plus x minus 12 equals 0. And this can be factored pretty easily. In fact, I'm going to do so. When we think about what two numbers multiply to make negative 12 and add to make 1, we recognize that it's going to be x plus positive 4 and x minus 3 that equals 0. So our two answers are x equals negative 4 and x equals 3. Done, right? But you may notice something a little bit strange about this answer. Look back at your two answers, and look back at the original problem. Is there an issue that we see with one of our answers? Well, the issue comes when we take a look at our right rational expression, 1 over x plus 4. If x is allowed to be negative 4, for instance, and we plug it in, we would get 1 over negative 4 plus 4. Negative 4 plus 4 is 0, and we get something that's not allowed to exist. We get 1 over 0, and we know that there are no rational expressions that are allowed to be over 0. It's not possible. What this means is, even though we solved and negative 4 looks like an answer, it would actually break our problem if it was. It's a false answer. It's an answer that looks like it works, but does not. There's a name for this that's given down below. If one of your answers is also in your restricted domain, meaning the things that x is not allowed to be, you get an extraneous solution. The good news is dealing with extraneous solutions is easier than finding them. To deal with an extraneous solution, just cross it off. Say that's not one of your answers. It can't be one of your answers. And that's it. Try out C on your own. Feel free to pause the video. I'm going to write down the answer in just a moment. How'd we do? If we take a look here, we do see our two answers are x equals 4 and x equals negative 1. Double check to see if these answers would still be okay in our denominators. If we plugged in 4 into both of these denominators, would it still work? Yeah, this denominator here would be 9, this denominator here would be 52. If we plugged in negative 1, this denominator would be 1, this denominator would be negative 3. These are both valid answers. Perfect. The second way of solving these types of problems is using the least common denominator. So let me give you a hypothetical here. Let's say I gave you the following problem. X over 5 minus 3 over 5 equals 12 over 5. How would you solve something like this? Well, you might say, Mr. Strager, we know that when we subtract and add with the same denominators, we're basically only doing it to the denominators. So in a sense, we can ignore the denominators since they're all the same. Our problem would just be x minus 3 equals 12. And then we know that x has to equal 15. When all your denominators are the same, you can treat the problem as if it's only doing math with the numerators, since the denominators are always going to have to be the same. This is the idea behind solving using the least common denominator. We're going to work through this next problem and see how it's done, because there are 4 main steps. So let's flip the page, everybody, and take a look at solving using the least common denominator. Here's the problem we're going to do together. 3 over x minus 1 over 2 equals 12 over x. Step 1 is figure out what your least common denominator is. So in this case, we know that our least common denominator has to have an x in the denominator, has to have a 2 in the denominator. Our LCD, our least common denominator, is 2x. So let's do what we did last lesson and multiply the fractions by what they need to make all their denominators the same. I'm going to do this work on a separate sheet of paper, and we'll compare it to see how the work down here goes. So if we need our denominators to be 2x, and we're starting with 3 over x minus 1 over 2 equals 12 over x, what can we do? Well, we would have to multiply this fraction by 2 on the top and bottom. We need to multiply this fraction by x on the top and the bottom, since we want it to be 2x. And we'd have to multiply this fraction by 2 on the top and the bottom. What we'd end up with after multiplying is 6 over 2x minus x over 2x equals 24 over 2x, which is exactly what we got here. Interestingly enough, what I decided to do in this step was I multiplied everything just by 2x instead of multiplying each individual term by what it needs. So in this problem, I just multiplied 3 times 2x, 1 times 2x, 12 times 2x, x times 2x, 2 times 2x, x times 2x. And yet, when we simplify those to make sure the denominators are the same, we all get the same answers as if we did it individually. Do whatever method you feel most familiar with. But since all these denominators are 2x, we can treat them as if they don't exist. We can just say 6 minus x equals 24. And when we subtract x from both, or 6 from both sides and divide by -1, we would get our answer, x equals -18. Now, this may be easier said than done. We know that with these problems, we might have to do some simplification first. So here's what I'd like you to do. I'd like you to try these 3 problems. I'm going to walk through each of them in a couple of seconds here. We'll come together and see how we did. So pause the video and try them out. Hopefully you've had a chance to try these problems out. Let's take a look at A. With A, we've got the denominators x plus 1, 2x, and 2x. So to make them all the same denominator, we should multiply them by what they need. Our first fraction here needs 2x. So we're going to multiply the top and bottom by 2x. This middle fraction here is missing an x plus 1. So I'm going to multiply it by x plus 1 on the top and bottom. And this last one is also missing an x plus 1. So I'm going to multiply that by x plus 1. We know that all of our denominators now are just going to be 2x times x plus 1, since we multiply them all out. 2x times x plus 1 for this one equals something over 2x times x plus 1. 2x times 3x we can write as 6x squared. So I'm going to do so. I'm going to write it as 6x squared. Yeah, I'll write this as 6x squared. 5 times x plus 1 we can write as 5x plus 5. And 3 times x plus 1 we can write as 3x plus 3. From here, the denominators disappear. So we essentially have the problem 6x squared minus 5x plus 5 equals 3x plus 3. We use our solving strategies from Unit 2 to move everything to the other side and distribute this negative. So let me distribute the negative first. 6x squared minus 5x minus 5, because we distributed the negative to everything, equals 3x plus 3. We're then going to subtract the 3x and the 3 from both sides, giving us 6x squared minus 8x minus 8 equals 0. And we can solve this one, hopefully, by trying to factor it. I'm going to do the factoring on a separate sheet of paper just because we're running a little low on space here. But if we wanted to factor this, we first have to take out the GCF, the greatest common factor. So the greatest common factor from all these is we can take out a 2. 2 times 3x squared, 3x squared minus 4x minus 4 equals 0. Then we can go forward and we can factor this using the AC method. So the AC method goes, multiply your A times your C, put it on the top of your combinator, solve the combinator part like normal. The two numbers that multiply to make negative 12 and add to make negative 4 are negative 6 and positive 2. So we rewrite our big problem here, 3x squared minus 4x minus 4, as 3x squared minus 6x plus 2x minus 4. From here, we know that we can factor this by grouping, so let's do it. We group our common terms, take out what's in common between them. So this is, we can take out a 3x from both of these. 3x, x minus 2. And from these two, we can take out a 2. So we do plus 2 times x minus 2 equals 0. We know then that our final factored form is going to be written like this. It's going to be written as 2 times 3x plus 2 times x minus 2 equals 0. We go through and set each piece equal to 0. So if x minus 2 equals 0, again I'm doing my work up here for lack of space, we could add 2 to both sides, giving us x equals 2. One of our answers is x equals 2. The other answer, we could set 3x plus 2 equal to 0 and start solving it. So we subtract 2 from both sides, giving us 3x equals negative 2. Divide both sides by 3 and get x equals negative 2/3. So x equals negative 2/3 is our other answer. Are any of these extraneous? Let's check our denominators. If I plugged in 2 for x plus 1, that'd be 3, so that's fine. If I plugged in here, it'd be 4, so that's fine. Negative 2/3 plus 1 is 1/3, so that's fine. Negative 2/3 times 2 is negative 4/3. So none of these result in our denominators being 0. Therefore, these are just our two answers for x. I'm going to solve the next problem on another sheet of paper just because it's going to be a little bit more lengthy and I don't want to try and cram it all into one space here. Now for this problem here, we see that we have an unfactored denominator. So our first step should always be to factor our denominators so we know what we're working with. What we have is, this is x minus 2 equals 6 over x squared minus 4. X squared minus 4 can be written as a difference of squares. So this is x minus 2 times x plus 2. And then we have this plus 1. which we know we can write as 1 over 1. What's each denominator lacking? Well, it looks like the least common denominator is x minus 2 times x plus 2. So this one here needs x plus 2 to multiply both of them. This one here doesn't need anything, but this one here needs both x minus 2 and x plus 2. So this is times x minus 2, x plus 2. What we end up getting is something that looks a little bit messy. We end up getting x plus 2 times 3x minus 2 equals 6 plus x minus 2 times x plus 2. And of course you could put all of these over x plus 2, x minus 2. I eliminated the denominators in the same step just so we don't have to write it all down again. This one is going to be a little bit of a pain to solve, but we know how to solve this. We can use FOIL. So let's FOIL this first one out. X times 3x is 3x squared. X times negative 2 is negative 2x. 2 times 3x gives us 6x. And 2 times negative 2 is minus 4. This equals 6 plus x squared minus 4, because we know that these two are a difference of squares. Sorry about the brief pause, y'all. I think I had to reset the video. So this is what we end up with when we end up distributing. 3x squared minus 2x plus 6x minus 4 equals 6 plus x squared minus 4, since we know that x minus 2 and x plus 2 will make x squared minus 4. When we combine like terms and move everything to the other side, we'll get something even simpler. So 3x squared plus, doesn't really look like a 2, plus 4x minus 4 equals 6. Sorry, not 6. It'll be 2 plus x squared, since we can combine 6 and minus 4. We can then move everything over to one side. So if we subtract 2 from both sides and x squared from both sides, we can subtract the 2 and we can subtract the x squared and end up with 2x squared plus 4x minus 6 equals 0. These will cancel out. From here, we can factor this as normal. We can factor out the 2, giving us x squared plus 2x minus 3. I apologize about the bell there. And we can ask, what numbers multiply to make negative 3 and add to make 2? It's going to be negative 3 and negative 1. So x plus 3, x minus 1. We now know our solutions. Our solutions to this problem, for problem number 2, are x equals negative 3 and x equals 1. So I'm going to write that down. X equals negative 3, x equals 1. Perfect. But we have to check for extraneous solutions. So, negative 3 minus 2, that's not 0, that's fine. Negative 3 squared minus 4 would give us 5, so that works out fine. We can do 1 minus 2 to get negative 1. 1 squared minus 4 to get negative 3. None of those are zeros, so this is just our answer. Very, very nice. Last but most certainly not least, we have problem C. Problem C is actually going to be a little bit of a quicker one, but let's see if it stays easy the entire time through. So I'm going to write this problem down so we can get started on a separate sheet of paper. This is 6 over x minus 3 equals 8x squared over x squared minus 9 minus 4x over x plus 3. Aha! We know that we can factor x squared minus 9 pretty quickly. X squared minus 9 is just x plus 3, x minus 3. It's a difference of squares. So we ask, what do the other terms need? Well, this one's missing an x plus 3, so I'm going to multiply my top and bottom by x plus 3. Then we have a missing x minus 3 in this one. We would end up with multiplying this by x minus 3 and this by x minus 3. All the denominators will look the same, so we can just get rid of them. We can just ignore them. And what we have is 6 times x plus 3 equals. We didn't need to multiply anything by our 8x squared term, so that's just going to stay 8x squared. Thank God. And 4x times x minus 3, we can just write as minus 4x, x minus 3. We can distribute these. When we distribute, we end up getting 6x plus 18 equals 8x squared minus 4x squared plus 12x. And once again, if we move everything over to the same side, in this particular problem, I think it'll be easiest for us to subtract the left side and move it over here. We would end up getting, these canceling out, we'd be left with 4x squared, since 8x squared minus 4x squared is 4x squared, plus 6x minus 18. Aha. This problem, we want to see if we can factor once again. So we take out the 2, since all of these can be divided by 2, giving us 2 times 2x squared plus 3x minus 9. And once again, we can use our AC method. Set up a combinator. Our A value is 2, our C value is negative 9. So we're looking for what multiplies to make negative 18 and what adds to make 3. Spoiler alert, it's 6 and negative 3. So finally, we can rewrite this as 2 times 2x squared. Let's do plus 6x minus 3x minus 9. We factor by grouping. We know the steps for factoring by grouping, but we know that we see what we could take out of the first group, what we could take out of the second group. This here will give us 2 times the quantity, 2x, parenthesis or bracket if you're using brackets, x plus 3, minus 3, brackets, x plus 3. Since we were able to take 2x out of these two and negative 3 out of those two. This means that our factored form for this problem, our factored form for what x equals, is as follows. 2 times 2x minus 3 times x plus 3 equals 0. Our two x values that would make this work we'll need to solve for. We know that to make x plus 3 0, it should be negative 3, because negative 3 plus 3 is 0. But over here on this one, we might need to set it equal to 0 to solve in case we don't know off the top of our heads. So if 2x minus 3 equals 0, we should add 3 to both sides, giving us 2x equals 3. Then divide by 2 on both sides. Our other number is 3/2. So our other answer is x equals 3/2. But we need to check for extraneous solutions. If we plug in 3/2, 3/2 minus 3, it's not 0. 3/2 squared minus 9 is 9/4 minus 9, it's not 0. And 3/2 plus 3 is 3 3/2. So that's good. Negative 3 minus 3 is negative 6. But as soon as we plug it into either one of these, we find an extraneous solution. Because think about it. Negative 3 plus 3 would make 0. And negative 3 squared minus 9, negative 3 squared is 9. 9 minus 9 is also 0. Negative 3 is an extraneous solution. So we say that our only answer is x equals 3/2. Beautiful. The last thing we're going to take a look at is tangentially related to what we've been doing here, mostly because we've been using our algebra skills, and this type of problem requires algebra skills. But we're going to talk about something called inverses. An inverse is a type of opposite. It's basically flipped around, you could say. The inverse of a function is found by changing your input variable into your output variable, and your output variable into your input. So you're changing x into y into x, and then solving to get y by itself. It's much better if we take a look at an example. So here's a function, f of x equals 2 over x plus 3. Recall that f of x is just another way of saying y, right? So we can write this as y equals 2 over x plus 3, right? Right. The inverse function uses this funky notation, f to the negative 1 power of x. It's a weird notation, but it works. To find the inverse, what we are going to do is we are going to change our y's into x's and our x's into y's. So when we rewrite this problem, we're going to move the x over here so it's by itself, equals 2 over y plus 3. Super strange. Now we need to solve this for y. And I'm going to show you a shortcut, and I'm going to show you the long way around. Let's do the long way around. First of all, to get y by itself, it can't be in a denominator. So what can I do to get it out of my denominator? If I multiply both sides by y plus 3, that will cancel out the denominator. See how it cancels out on this side? We'd be left with x times y plus 3 equals 2. Now y is on top. There's no fractions left. So let's try to get y by itself. We start by dividing by x, because that'll get rid of the x on this side. So y plus 3 equals 2 over x. And last but most certainly not least, we can subtract 3 on both sides to get y all alone. We found y equals 2 over x minus 3. And since they wanted it in function notation here, we could write it as f to the negative 1 power of x equals 2 over x minus 3. These are the same thing. I promised I'd show you a shortcut, and I am. So here's the shortcut box. Anytime you have one thing equaling a fraction, and this works for any problem. Whoops, this is a y, not an x. Sorry. Anytime you have one thing equaling a fraction, the shortcut is that you are allowed to switch the entire other side with the denominator to simplify. If we switched x and y plus 3, wouldn't we get y plus 3 equals 2 over x? And that's what we had in this step. It's a shortcut. But you have to remember, you have to switch the entire side by the denominator, not just what you want to switch. That is it for the video, everybody. So thank you so much for listening in, and as always, have a fantastic rest of your day.